Next in our series of videos is one about Ampere's law. And Ampere's law describes how a magnetic field is created a distance from a current carrying wire. If you've done the reading, you've already seen the equation for Ampere's law. It is B, the magnitude of the magnetic field, is equal to mu naught times the current divided by 2 pi r. And if you look at that equation, it may look a little familiar. It is a field that is directly proportional to that concept which creates the field, and it is inversely proportional to the distance from where that is happening. But of course, I'm sure you've also noticed that unlike other similar equations, here it is inversely proportional to r and not to r squared. So we're going to talk about why that is in this little discussion. When we talk about the magnetic field B at some distance r away, we're talking about the field created some distance r from our current carrying wire. There's a big difference between a field created by a current carrying wire and, say, an electric field created by a single charged particle, or a gravitational field created by a single mass. Our current is creating the field, and there's a really big difference about that. So why don't you think about what that difference might be, and of course hit your pause button. And now we're back from your pause, and what do you think? Why is it different? Why do we not have r squared in the denominator in this equation? Well, if you said that it's because the magnetic field created is due not just to this charge that's moving in the line of current, but also to this charge that's moving in the line of current, and also due to this charge that's moving in the line of current. Well, if you thought that that's why we have r and not r squared, you're absolutely right. If you're taking calculus now, you might notice that 1 over r squared, when integrated, gives you something with a 1 over r in it. And if you were thinking along those terms, you were thinking exactly correctly. So let's go back to the equation. When we look at this equation, we see that we've got, of course, the current that is the moving charge that creates the field. We have the distance from the wire, and that, of course, is measured on the perpendicular to the wire. And we have this new little fellow here, new in our conversations. This is, you'll recognize the Greek letter mu, and the subscript, a little 0, and we say that aloud, mu naught. And mu naught is called the permeability of free space. With a name like permeability of free space, I hope it brings to mind another concept we've seen of late. So take a moment, think about what that concept is, and we'll be back together in just a few seconds. Okay, were you thinking, did this remind you perhaps, did mu naught remind you of epsilon naught? You remember epsilon naught, which is the permittivity of free space. And we saw that is very much akin, as we saw in our discussion of capacitors recently, that's very much like what Coulomb's constant represents. And of course, we remember that epsilon naught is just 1 over 4 pi times Coulomb's constant. But let's talk about mu naught. our new friend, the permeability of free space, which of course we need to identify not just with its value, but of course, as we always do, with its units. So let's think about the equation. And ask ourselves, what must the units of mu naught be? Take a moment to think about that. And we're back. So, after you gave that some thought, what must the units for mu naught be? Well, we're taking something, we're multiplying it by a current, we're dividing it by 2 pi r, a unitless value, another unitless value, and a value in meters. So mu naught must have the units that would give us Tesla if we multiply it by a current and divide it by a distance. So of course, that is Tesla meters per ampere. And mu naught has one of the more interesting values in all of physics. Someday I hope you'll get to take a far more advanced physics class where you can find out why it has such a interesting value. But it is 4 pi times 10 to the negative 7 Tesla meters per ampere. And when I first saw that, I thought maybe it's, sort of like 4 pi times 10 to the negative 7, so they just called it that, like it's 13.56 times 10 to the negative, 12.56 times 10 to the negative 7. But no, it's exactly 4 pi times 10 to the negative 7. A really neat thing. Of all the constants of nature, it's the one that we know to the greatest precision because it's a integer multiple of pi. Okay, so that is our equation for the B field, a distance from a current carrying wire. More on this in a future video.